La la la. Okay. I'll begin with a word of prayer. I've resolved my technical difficulties back there. So, dear Heavenly Father, we thank you for this day. Thank you for these students. Just ask you just bless our work today, Lord. In your name I pray. Amen. So today we're talking about absolute convergence and alternating series. So let's talk about absolute convergence to start with. Definition: a series sum over a sub n is absolutely convergent if the corresponding series of absolute values is convergent. All right, so this is absolute convergence. Let me give you an example. If we had something like let's say S equals to 1 minus a third minus a ninth plus a 27th plus an 81st plus a 1 over, I don't know, what is that, 3 to the 5th. So I've got 2 minuses, now I've got 3 pluses, and then the next I've got the same pattern but with 4 minuses, right? So like so this is not a geometric series, right? It's not geometric because what? Depending on where you are, you're either multiplying by a third or minus a third to get to the next term, right? But it's not regular. It's like not always multiplying by a third. It's not always multiplying by minus 1/3. So it's not geometric, right? But it's kind of like a geometric series, right? If you take the absolute value of this, so here, I don't want to write the formula down, right? I just want to say that this is the sum n equals 1 to infinity of a sub n, all right? So I'm thinking, like this is a1. This is, a2 is minus a third, etc. Right? Then if you look at this series, what is the sum n equals 1 to infinity of the absolute value of a sub n equal to? It's just 1 plus a third plus a ninth plus a 27th and so forth and so on, right? In other words, if I take the absolute value of the series, term by term, it's what? What kind of series is this? It's geometric. It's geometric with what? A equals to 1, R equals to 1/3, right? Which is a convergent radius. And so we know this, not only this converges, we can say what it converges to. It converges to 1 over 1 minus a third, otherwise known as 1 over 2/3. In fact, this series, not the given series, but the absolute value of the series, term by term, converges. So what's this say? This says, therefore, S is absolutely convergent. There's a theorem which says the following: absolute convergence implies, well, absolute convergence of the series a sub n implies convergence of the same series. All right? The proof of this won't take us long. All right? Let's look at the proof of this theorem. So if this theorem is true, what does it tell us about example 1? Once we know this theorem, what can we say about example 1? S is a what? It's a convergent series, right? Yeah. Okay. So the proof here, for each, I'll do n. We have minus the absolute value of a sub n is less than or equal to a sub n is less than or equal to the absolute value of a sub n. Which tells me what? That tells me that 0 is less than or equal to the absolute value of a sub n plus a sub n is less than or equal to twice the absolute value of a sub n. Okay, so this is an estimate which is always available in comparing a series to the absolute value term by term of the series, right? This is just truth about absolute value. So then, consider if the sum of the absolute value of a sub n converges, then by the direct comparison test and the inequality right above, right? Let me give it a name. By the direct comparison test and the above inequality star, we find what? That the sum of the absolute value of a sub n plus a sub n converges, right? By comparison to what? 2 times the sum of a sub n, right? And this converges, right? We're assuming that that converges. Yeah? So then what was that? Great, that's not what I want. What am I trying to prove? I'm trying to argue that the series with term a sub n converges, right? So at the moment, I have that the sum of an and absolute value of an converges, right? So here's the trick. So next up, just notice that a sub n is equal to what? It's equal to a sub n plus the absolute value of a sub n minus the absolute value of a sub n, right? And so that shows me that the series formed by a sub n can be understood as the sum of the series formed by an plus the absolute value of an minus the series of the absolute values of an. All right? But both of the things I wrote on the right-hand side, we've already shown converge. Or we've assumed that they converge because that's the precondition of the theorem, which then shows you, of course, that a sub n, the series formed by a sub n, converges, right? This converges. This is convergence. It converges by assumption. The difference of convergent series is, again, a convergent series. All right. So again, in words, the theorem simply says absolutely convergent series are convergent. Where is this useful in terms of problems? Like what kind of problems, what kind of problems would not be suitable for tests we've looked at in previous classes. Yeah, negative values, right? Because like the limit comparison and direct comparison, and I think the current form of the root and the ratio test have all been for what? For series with positive terms. There is a version of the root and ratio test which doesn't require positive terms, but then you have to take the absolute value of the terms for the root and ratio test. Let me talk about that another day. I don't want to talk about that right now, but so this is definitely useful if we have some minuses that are, thrown into the formula for the series, and you can kind of see past it. If you could get rid of the minuses, you've just got something that you already know converges. Well, absolute convergence is the right tool for that kind of problem. Yeah.
You have to combine other tests to this one in order to solve this problem.
Sure. Yes. Yeah. I mean, it is definitely possible that we need to take the concept of absolute convergence and, well, I mean, this time we paired it with geometric series, right? So, yeah. All right. So, yep.
If you find the absolute convergence of the series, or absolute, if the absolute size of it suggests anything about the original?
It does not. So, it may or may not. So, a couple of examples. I'll explain shortly that if we looked at point number 1, if we look at sum n equals 1 to infinity of, say, minus 1 to the n plus 1 over n, which is 1 minus a half plus a third minus a fourth plus dot, 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 dot. So is this series is definitely not absolutely convergent, right? Why? Yeah, if we have a sub n is minus 1 to the n plus 1 over n, then the absolute value of an is just 1 over n. And, of course, we know that the sum n equals 1 to infinity of 1 over n is the divergent, right? P equals 1 series. So the gentleman was asking me a question, if the absolute value of your series term by term diverges, does it tell you anything about the possible convergence or divergence of the original series, right? And so, this one, it turns out we're going to be able to argue that this series is in fact convergent. All right. The series that I'm looking at here is the so-called alternating harmonic series. So we have a test which proves that it's convergent, but I think it's useful actually to just talk directly about why this series is convergent by studying its partial sums. All right, let's do that. Let's study the partial sums of the alternating harmonic series. So what's the first partial sum? Just 1, right? What's the second partial sum? 1 minus a half, which is what? 0.5, right? What's the third partial sum? 1 minus a half plus a third, right? What's that? think that's 0.8333 repeating, right? What's the fourth partial sum? Well, it's S3 minus a fourth, right? Which is approximately, so I have to subtract 0.25. What's that? What's 83 minus 25? I heard a 58. Can somebody give me the third digit? It's just 3333, right? And then what's S5? It would be S4 plus 1/5, right? Which is 0.78333333. And then S6, we subtract a sixth, right? Now, let me draw a picture of what's going on here. So here's 1. Here's 0. So on this number line, where is S2? It's right in the middle, right? Here's S1 over there, right? Where's S3? 0.83, so it's like, I don't know, here-ish. Where is S4? 0.58, so it's kind of like over here-ish. Where is S5? 7.8, so it's, man, it's close to this S3, but it's a little bit below it. And then what happens with S6? It's minus a sixth, right? So it doesn't make it past S4, does it? Like it doesn't make it past there. So S6 looks like this, S7 like that, S8 like that, S9 like that, 10, 11, 12, See, they're homing in on some point in there somewhere where the red dashes are, right? If you keep studying this carefully, doing more numerical exploration of this problem, what you find is the place it's homing into is about 0.692-ish. So it's not a proof, but perhaps it's a plausibility argument that in fact the alternating harmonic series is a convergent series, right? Yet it's not absolutely convergent, right? Because the absolute value term by term gives us the harmonic series, which diverges. So convergence and absolute convergence are not the same thing, right? These are distinct concepts. An example like this is by definition conditionally convergent. A series which is convergent but not absolutely convergent is a conditionally convergent series. So conditionally convergent series are kind of like right on the bubble. They're an alternating series, which I'll define shortly, all right? Which is just kind of barely convergent in some sense. Hey, do you guys know what 0.692 is? Recognize? Yeah?
In my chem homework last night, it was like LNFs.
Ah, from chemistry last night, natural log of 2. Very good number sense. That is true. That is, in fact, what it converges to, the natural log of 2. Why on earth is that true? Well, this is, all right, so I've shared with you a couple of weird results about, what I'm saying is that dot, 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 this is equal to the natural log of 2. Great. Why? This actually I will give you an explanation for in here. In contrast, it'll be quite a while before I explain to you why this one is pi squared over 6. So this is a much more mysterious factoid. This actually we will find the tools to prove after the next test. Okay? Okay. So this is, yep.
Why is it convergent if it's a p equals 1 series?
Why is it divergent if it's a p equals 1 series? This is part of the p series result, remember? We had the general, the other day we proved that the sum n equals 1 to infinity of 1 over n to the p. Here's how it breaks down. Divergent for p less than or equal to 1, convergent for p greater than 1.
I thought it just converged to L2.
This is not the same series. This is the alternating harmonic series. It's got plus minus in it. See, this, and what I'm trying to say is 1 plus a half plus a third plus dot, 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 versus 1 minus a half plus a third minus a fourth plus dot, 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 dot. Divergent, convergent. These are not the same series. One's got the plus minus going on, one doesn't. Not having the plus minus going on makes this partial sum keep growing and growing ever so slowly, like I shared with you guys yesterday, right? Like even to get to 20, we had to go stupidly far out in the partial sums to get that far, but it does keep growing. Okay, so I should define for you an alternating series. This is an example of an alternating series, thus the terminology alternating harmonic series. What is an alternating series? Definition: if S equals to something like A0 minus A1 plus A2 minus A3 plus dot, 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 dot. In other words, it can be written as the sum n equals 0 to infinity of minus 1 to the n. And I'm following. All right, so here's the question is, do you want me to stick with, I guess I will. Honestly, folks, I'm going to, in order to make better contact with all of my old solutions and such, I'm going to divorce myself from the notation of Salas and Hilly right here, because I traditionally have always used b sub 0, b sub 1, b sub 2, b sub 3 like this, and I'll explain the connection here. B sub n, where b sub n are positive, okay? The reason I do this is because then I can tell you, an alternating series, in other words, then S is alternating. So the reason for me not using the same letters as he does is because I like to be able to write the following. I like to be able to say an alternating series has a sub n equal to like minus 1 to the n times b sub n, where the b sub n are positive. So I like to keep using a sub n for like my generic term in the series, So if I use the notation he's used here, it kind of puts me in a pickle. Anyway, I care much more about this issue than you do. An alternating series is just one that goes plus, minus, plus, minus. Now, you're like, what if it goes minus, plus, minus, plus? Is that still alternating? Yes, right? I mean, so you could start with minus. It could start from like 5 instead of 0. Like these things we don't
think of as really being different. This is just what I've written down, right? I mean, you could just as well start at 10 with a minus and then go plus minus from there. Do you want me to write this out formally, or can we agree to understand what I'm saying? Would an example help? Maybe? I don't know. What example am I on? 3? 2? I feel like this is example 3. Although I didn't really label, this was example 2, wasn't it? And it wasn't in examples. It was really just one example, wasn't it? Okay. All right. So example 3, we could have something like this. The sum, say n equals 7 to infinity minus 1 to the n plus 1 over n squared. So that would be like 1 over 49 minus 1 over 64 plus 1 over 81, dot, dot, dot. This is an alternating series. If you want me to do some name calling here, I would say that this is the tail of alternating p equals 2 series. All right. So what's the theorem? What's the theorem about alternating series? All right. So the concept of absolute convergence is a little bit different than this in the sense that, like absolute convergence, we're taking a given problem, we're modifying it, we're taking a related problem and seeing whether or not that can converge in order to say something about the original series, right? In contrast, we might just be given an alternating series, and in that case, we can apply the alternating series test. Or AST, all right? And it's wonderfully simple, wonderfully simple. So let B0, B1, B2, da 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 be positive. Positive terms. Then the series B0 minus B1 plus B2 minus B3 plus dot 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 dot. In other words, equals to the sum minus 1 to the n, a sub n equals 0 to infinity, all right, converges, fill in the blank. And I'll put a if and only if here. What? There's supposed to be a b sub n in my language here. If and only if what? It's shockingly simple, but all that's required is that b sub n goes to 0 as n goes to infinity. Yep. Still writing it. Sorry. Good question. Yeah.
It's still an alternating series if it goes plus plus minus minus.
If it goes plus plus minus minus plus plus minus minus, no, it is not an alternating series. We got to have plus minus plus minus plus minus plus minus. Although If we did have a plus plus minus minus plus plus minus minus plus plus minus minus series, we probably could play games with it to make that into a sum of two alternating series, right? Like take the even and odd subseries or something like that. But this is dangerous for the following reason. Theorem. This is Riemann, 1867. He proved that you can take a conditionally convergent series. All right? You can take a conditionally convergent series, and you can just shift terms around. If you rearrange the order in which you're adding them, so in other words, like, you know, maybe take this third and just add it over here somewhere. And, you know, take this fourth and add it over here somewhere. Just rearrange the order in which you're adding things. That shouldn't matter, right? No, it does. You can prove that by a rearrangement, you can make a conditionally convergent series converge to any real number. Or, as the book mentions, you could even make it not converge. You could rearrange it in such a way that it oscillates between two bounds. So conditionally convergent series are very delicate, and if you like rearrange them, you change where they're going to. So a series is not just its sum, it's the order in which things are being added. Yeah? And, but good news, a absolutely convergent series is immune to Riemann's rearrangement lemma. In other words, any possible rearrangement of an absolutely convergent series won't change the value of the series to which it converges. So we like absolute convergence in terms of manipulation of series. Conditionally convergent series, if you rearrange the terms, you can actually change the answer. All right. I shut up. So the alternating series test right here is stated. What's the proof of this? You're like, yay, another proof. Hey, this is our last one, so relax. So, I mean, for this part of the course, proof, if the sum minus 1 to the n, b sub n equals 0 to infinity converges, right? Then minus 1 to the n, b sub n goes to 0 by the nth term test for convergence, right? Yep. Oh, I'm definitely proving the AST test. I do not want to prove Riemann's rearrangement lemma. No. It's not, you know, for you math majors, it's not that bad, but it would require me like formally defining what we mean by rearrangement. It's just a rabbit that we don't want to chase today. So if, thank you, very, very good question. If this series converges, then it implies that this goes to 0, right? But that implies that that b sub n goes to 0, right? So that's the forward direction of this arrow, right? We've just this direction of the proof. All right, so now we study the other direction. Suppose that b sub n goes to 0. And he says, look at S sub, let's say, 2k. All right? So if we look at S sub, the even partial sum, S sub 2k, well, that would be equal to b0 minus b1 plus b2 minus b3 plus plus a sub, oh, good grief, b sub 2k minus 2 minus b sub 2k minus 1 plus b sub 2k. So in other words, I'm saying look at n equals to 2k. Look at the even terms, the subsequence of even terms in the partial sum. What are you looking at then here? What can we say about this? If Bn limits to 0, right? And Bn is positive, what does that say about the sequence B sub n? Is it increasing? Is it decreasing? What is it? It must be decreasing, right? Otherwise it couldn't have limit 0. Hence, what? What does that say about all these terms? If B is decreasing, these are all. I think I heard a positive, right? These are all positive terms, right? And this is by assumption positive, which shows you what? S sub 2k is positive, I think. I think we can say more than that. Well, I mean, it's positive, but what else can we say? Also, he points out that S sub 2k plus 2 is equal to S sub 2k minus parentheses B sub 2k plus 1 minus B sub 2k plus 2. Hence, S sub 2m plus 2 is less than S sub 2m. So what's he arguing here? He's arguing that the sequence of partial sums of even index is a decreasing sequence of positive numbers. We saw this over here in my example, right? Oh, see, this is the... Ah, man. It's going to be flip-flop for my example. Why? What's the difference between my example 2 and the proof we're going through right now is the way that it starts, right? Yeah, it's arranged so that this is arranged so that we've got positive on the even, right? This one is arranged so that we have positive on the odds. See? Right? So the story turns over for this. And this one, the even subsequence is an increasing partial sums. The odd subsequence is a decreasing partial sums, right? And anyway, so anyway, getting to the point here, we have what do we have? We have a positive sequence of what? Decreasing partial sums. Therefore, we can apply the bounded monotonic sequence theorem that says that the sequence of even partial sums converges to 0. Because 0 is the what? The what? What is it? The greatest lower bound, right? Well, I can't say that it converges to 0, but I can say it follows. I should say it follows that S sub 2k converges to L. I think I'm running out of time to do this properly here. Yeah, you guys are making me nervous here. All right. How about the odd partial sum? We're almost done here. S sub 2m plus 1 is equal to S sub 2m minus A sub 2m plus 1, right? And, oh, okay, so that's just, the thing I just wrote is immediately obvious, right? just from the setup of the series, right? We're subtracting odd terms, so we get the even partial sum to get to the odd partial, the next odd partial sum. We just add the next term in the sequence, but here that goes to, this. Oh man, what's wrong? This is very silly. What did I do? This A is supposed to be what? B, right. So if you look at what I have right here, you guys tell me, why is it, oh, I'm sorry, I seem to have, let me make some corrections in red. I was trying to stick with K here, and I have inadvertently switched it to an N one place. So I want K's, 2K plus 1, S sub 2K, B sub 2K plus 1. So you guys tell me, what happens to S sub 2K plus 1 goes to what as K goes to infinity? So what do we know? We know that B sub 2K plus 1 goes to what? Goes to 0. And we know that the even subsequence, we've already argued by the bounded monotonic sequence theorem, that it is converging to something. We've called that something L. So what's this prove? If the B sub 2K plus 1 goes to 0, and the S sub 2K goes to L, it follows that the odd partial sum also goes to L, right? So fill in the blank L. And then we need a homework exercise which says that if you have a series, or if you have a sequence rather, and you can prove both the even terms of the sequence limit to L and the odd terms in the sequence limit to L, it follows that the entire sequence limits to L. So that's the proof. And if I've muddled it, my apologies. It's really written nice and cleanly in the textbook handout that I gave you guys on page 599. All right. Now, there is also an alternating series estimation theorem. How do you bound the error in an alternating series? Here's the alternating series estimation theorem. It says the following: if the sum n equals, let's say, 0 to infinity of like minus 1 to the n, b sub n is alternating series, let's say convergent. A convergent alternating series, then if you take the sum n equals 0 to, you guys pick a letter, any letter. What do you want? P? All right, sure, why not? P, minus 1 to the n, b sub n. Well, the whole series, all right? Take the whole series, subtract the pth partial sum, all right? The absolute value of this, in other words, this is TP. This is TP for the alternating series in question. That's the tail, right? Formed by taking the whole series and subtracting off the pth partial sum. Okay? Now we bounded that error looking at with the integral test, right? That does not apply here because why? Not a series of positive terms, right? We can't do that integral test here. And you know what? Thank goodness we don't need to, because the alternating series estimation theorem, if I have to test on estimation, I usually test on this because it's so stupidly simple. You could already see it in my example too. S3 was what? 0.833, right? the actual place it converges to is 0.692. What comes next? 1/4, right? So the theorem is simply this. If you look at the pth partial sum, you're within the bp plus 1 of the answer. So the error is bounded by the next term you haven't used. It's just that. No integral. I mean, what could be simpler? This is the alternating series estimation theorem. And the proof is really no different than my example 2, just done in the abstract, okay? So. All right, so let's take stock in what we have done so far. I've covered a number of convergence and divergence theorems for you, right? I will read for you a paragraph from page 596 of the handout. This paragraph is wonderful. It says, in general, the root test is used if only powers are involved. The ratio test is particularly effective when factorials and combination of powers and factorials. It says, if the terms are rational functions in K, the ratio test is inconclusive, and the root test is a pain. All right? He says difficult to apply, but let's say it's a pain. Series with rational terms are most easily handled by the limit comparison with a p-series. That is a series of the form 1 over k to the p. If the terms have the configuration of a derivative, maybe we could apply the integral test, all right? But we have to keep in mind always, and this is our first line of defense, that if the kth term does not go to 0, then, as we discussed day 1, it diverges, right? That kth term divergence test, or nth term. So past this, we've added just a couple more tools today, right? Absolute convergence and the alternating series test, which is the simplest in some sense of the ones we've covered lately, because it just says if it's alternating and the nth term goes to 0, guess what? Game over, converges. What happens if the nth term does not go to 0? That puts us back in day 1. That's the nth term test. It diverges, right? So tomorrow I'm going to come and show you 3 more divergence tests. No, not true. This is it. That's all she wrote. I mean, that's it for our divergence tests. The only thing I can really add to this is discuss the absolute convergence and the root and ratio test. There's a combining of those two concepts, which is particularly beautiful. We should talk a little bit about, but that's pretty much it. So it's time to start doing homework, is what I'm trying to tell you. That's it for the next test.